In this video, I'm going to show you some interesting insights about my rendering journey of a milling coin. In the previous video, we unlocked rendering thousands of them by leveraging Unity particle system. Let's crank up things a little bit this time, shall we? As this technique will completely dwarf the previous one in terms of performance and flexibility. I also highly recommend you to take a look at my 7-minute walkthrough of indirect GPUInstancing. But if you're well aware of that technique, let's dive into some practical implementation of it right now. Before we start, let's divide the task into several parts. First, we need to make a compute shader to make the spawn point cluster look like a natural pile. Then we will have all the flexibility to swap the geometry, so next up we spawn the gold coin on the pile of data. With some pixel shader work, its appearance can look more believable. Don't forget to give it a physically correct posture. Well, of course, make sure your computer doesn't explode during the time as a side quest. Let's get started. The first step is to spawn the instance point in some reasonable and regulated way. By reasonable, I mean, although we are creating a mountain of it, we only care about populating the outer 2D surface. Well, I argue that Poisson distribution does provide a more natural look, but it is pretty hard to implement in parallel computing, as you can see from its sequential nature. There is a way to implement a throwing dart algorithm on the GPU to parallelly create that effect, but it mainly works well with pixels. Here I have an array of pixels contained in the render texture displaying a pseudo noise. Just to showcase that if very high precision is needed, such as our case, the resolution of the texture is going to be very high. To demonstrate, I have a 512 texture holding dots with around 30% of activation rate. Each red pixel represents the space of one object. If each pixel represents 1 cm of accuracy, this whole lot of data can only map to a half meter squared area, making this approach very hard to scale. We can always fall back to the grid spawn as a starting point, and then add a random XZ offset to break the uniformity. The XZ offset makes sure each spawn point stayed within its unit. On the large scale, it can also achieve a nice homogeneous randomness. Next up, for ease of control and optimization purpose, I introduced a unit called tile, representing the smallest size of a collection of units in our project. Each tile can hold an integer power of 2 amount of instances, such as 1, 4, 9, etc. The tiles can sample from other buffers that hold supportive data, like a scrolling noise or random color masks, or a combination of multiple of them. You can see that the spawn point can inherit the tile's property. More importantly, multiple instances can sample from a single calculation result, so we don't need to calculate 1,000 times more on pixels and vertex shaders. Then, it's about adding the third dimension. My original approach is to recycle my old finicky mesh generator. The mesh takes shape by sampling a Purdy noise, as it can quickly look very alike as Backroom Level 94. And great, as we might as well spend the eternity there tweaking the look. Well, the spawn point at least are sitting very nicely on top of the ground. Since we are using the mesh vertices data to fuse the point directly at the surface, but I'm not a huge fan of this dependency, I'd rather have a bit more control for the height, so I create a custom tool to capture the linear depth map of a Blender model terrain. This height map will then be converted to a buffer for our spawn points to sample from. The pixels on the height map are directly fed into our tile structure, so our instances can sample from it nicely. With the terrain start to take shape, we see a huge problem. The pixels are not continuous at all, so the surface is not smooth. I came across this scenery as I exaggerated the height map value. One way to fix this is to find each pixel's neighbor, and using the average vertex to do a bilinear interpolation and place the spawn point along the gradient. Well, on paper it is easy, unless you mess up a big time like I did. Please enjoy this scenery of happy accident. Well, eventually I made it work. I will show you an animation to prove that I removed the Minecraftness of the scene. The point now sits very nicely on top of the mesh surface, even with extreme slope. At that point of my development, I can't wait to replace the spawn point with some actual geometry to render and call it a day. Well, let's just crank up the instance count and witness how good it performs. Since someone said that the performance is the killer feature of this project, well, one thing I forgot to mention, if we choose to take a route of indirect instancing, you have to implement culling and optimization manually. Currently, all of the milling coins are being rendered even if the camera is on the moon and facing backward. Instead of that, we want the rendering result look something like those. So how do we achieve it though? Well, I have a short animation to walk you through the prefix sum GPU algorithm that is doing the heavy lifting behind the scene. The transparent frustum represents the camera, and currently there's nothing in view. As I move the camera, the actual objects that needs to be rendered are labeled as green. How can we rid of the red object? Remember, at this point, only the GPU knows the data, so we can't do it sequentially. Why don't we abstract them to the form of a linear array to prepare a visualization? Cool. Now let's see the parallel prefix sum in action. And you will see why to use prefix sum later. Let's break it down what happened on the second recording. All the cyan color cube represent the number is a result of an addition. As the pass number increases, you can see how the padding increases 2 to the power of that number. And on the second half of the algorithm, the padding decreases in the reverse fashion. All the yellow cube here represents the number is a result of a swap, resulting in this tree-like structure. At the end, only the first and the last arrays are preserved. Each element of the second array holds the sum of all the number from 0 to the previous of the element of the first array. Then, we use the first array as a mask to filter out all the zeros. Now, no numbers are duplicated in the second array, so they can become the index of a newly constructed array. And that array will be sent as the final buffer to render, resulting only the green object left on the screen. This chapter definitely deserves its own topic, and this implementation is actually not the most optimum, since it introduced something called the bank conflict. But for now, I just have to tell you that this animation visualizes all the code in this page that no one wants to write. But good news, there is a way simpler method called append buffer that basically achieves the same thing. The only drawback is it doesn't preserve the object's order. To demonstrate object drawn from the append buffer is random, I set up a control test. The two culling methods behave exactly the same when they are drawing opaque geometry, but when it comes to alpha blending, since order matters, you can visualize the result from the append buffer accumulation is totally random. The detailed implementation I have to leave to you to explore, and trust me, it's very trivial. Now, all types of culling such as frustum culling, distant culling, mask culling, and even occlusion culling can be handily enabled. We just need to append different return conditions before elements in the initial buffer is added to the append buffer. With some tweaks, the game can now run at a much more comfortable frame rate with a still decent object density. However, keep in mind this is just the beginning of the optimization. On the memory side, remember, even though we are calling out the red object from rendering already, their data are not being used, but still junking our memories. If we increase the object density, the memory size can quickly rise out of control. The idea is to break down the huge buffer into multiple smaller ones, as it will completely discard the chunks that's not being used. I'm not going to bore you with all the repetitive math behind it, and I did mess up a lot of time, as evident in those footages. But eventually I made it work, and this over-engineered version can be cleaned up a lot in the future. Here is a free statistic table looking scenery to show you that chunking and culling are working together nicely. Finally, we can safely replace the spawn points with the actual gold coins, but it doesn't take long to realize that all the coins are sharing the exact same rotation. Remember we spent a lot of time calculating the smooth height map? We can get a ground normal almost for free by doing a cross product between the neighbor heights. Currently, I'm actually displaying the color value of the ground normal. Seems pretty hard to tell, but these blue and yellow tints might give you a hint. Here, we spawn a bunch of visual indicators showcasing the directionality, looking pretty fun from far away. Now, officially, we are having everything ready. Let me show you how all the data are funneled together and contributed to the final effect. We firstly replace the utility shading with unlit texture samples. Then, we introduce PBR shading using the function I mentioned multiple times in part 1. Next up, we rotate the coin along its local apexes to break some uniformity. Following that, align the coin with the world space ground normal and enjoy how much of an improvement it adds to the lighting. And don't forget to add a bit more randomness to the pitch and yaw. And then that's it. Pretty ironic that the actual rendering part of the coin only takes about 30 seconds. This is only the start of what you can do. There are endless layers of effects you can add on to this system, such as adding clumping data if you want to render foliage, simulating interaction, and so on. I might consider discussing them in future project walkthroughs if you get a chance. One of the best things you can do to a gold coin is to duplicate it a million times. I have to say, to some extent, we've achieved that. Why not just use VFX graphs to do it fast and simple, you may ask? It might be the same reason why we still have manual drives in a world full of self-driving Teslas. That's it! Leave a comment and let me know your thoughts. Until next time, start to use RenderDocs to view your cat pictures.